if there is no sound. Testing sound. Now there's sound. Okay, so the entire introduction went over, and now there's even feedback. Okay, great. Right, so I'm going to do it again. So this is demo day for batch 27 of DSR. There is a theme, which is generative models for using unstructured data, doing tasks that are very human, like generating dance moves, generating text, and generating synthesizer patches. DSR is the longest running company training people in machine learning in Europe. We've been doing this for 7 years. And we do this with a method, which is getting people from industry to teach the one thing that they know very well and teach just that. Then we have 25 teachers. Each of them teaches the one thing that they know very well and leave. So the other thing that makes us different is that we put a lot of emphasis on portfolio projects. So we want our graduates to be able to solve real problems, and we do that by asking them to solve one before they graduate, which is exactly what you're going to see right now. So in the next 4 projects, you will see how people, after taking classes, did in mostly 2 weeks, a project that solves a real problem with machine learning. Right. So that's DSR, in case you didn't know. Most likely, if you're here, you already know about us. Let me introduce you to the first project. It's, we call them affectionately the Mohammeds, because there are 2 Mohammeds doing this. And it's called Dance Machine. It's answering the question of what happens if you could generate original moves from previous dance positions, right? I'm going to just pass the mic to the Mohammeds.
Okay, thank you so much, Jose. Thank you, everyone. Welcome to our project, the Dance Machine. I would like, in the beginning, to give you an overview of what is a dance machine. It's basically a generator, but what does it generate? It generates moves, general movements. It not only dance, it can generate any kind of movements. Basically, you input some past movements, and it gives you future movements. So now I will show you overview of our presentation. If you can help me with, it's not. Can you help me? Yes, as you can see here, this is the outline of our presentation. Yeah, this is the outline of the presentation that we will talk about. What we want to explain first, why are we doing this project? The reason why we are doing this project, in the gaming industry and animation industry and movies generally, there are so many advancements now that people are competing to make the best real movement of animation or animals. As you can see here, it's easier to make creature movements or animated characters. You can see the amount of effort and time that is being spent to reach that. And basically our idea is to train a model that can make this animation without making all of this effort. Another use case is to reanimate characters that does not exist anymore. For example, like Charlie Chaplin or Michael Jackson, by training our model into learning their moves and then be able to generate new movements. And for any machine learning problem, we try first to discuss the feasibility of this problem. And to discuss the feasibility of this problem, we have to ask ourselves if humans can dance, or like how human can dance. Can you help? Okay, so how can human learn dancing? The average human, when he wants to learn a dance, what he does? He basically watch a video of a dancer or watch a dancer, and at the beginning he tries to mimic this person. And only then he can start to make this dance. However, this is not making him a dancer. What he needs actually is to watch many videos and to train as many times as possible. So in the end, he is able to have a general sense of the movement of this dance. And from there, we decided to do our model in the same way. How can a machine learn dancing? Our approach is compiling as many videos of a certain dance as possible, and then let our machine learn these videos, train it, and then we are able to predict or generate new movements that's based on the style that it had learned. One of the generative models else that are existing in the market right now, many generation models like text generation, image generation, audio, like text generation, like GPT-2, for example. Everyone are using it right now in Google or emails or chat. It predicts what you want to say by inputting the past input. What about movement prediction? In our case, we have some challenges. To predict new movements, we will need to detect the movement of a person in a video and to train our model as well on the detected data. After that, we will be able to generate new movements. So our approach basically is divided into 6 parts. First, gathering the data, getting as much videos as we can of dances, and then post-detection, where we can detect the movement in this data. After that, loading the data into our training model, and then we can predict or generate new movements. And after that, we can visualize these movements into animation if you wish. For the gathering data part, as you can see here, we could gather about 10 hours of dancing, solo dancing person into a compiled video. And from there, if you look at the videos, we are not really interested to get all the video. However, we are only interested in getting the movement of the person in this video. And to do so, we used an open source library called MediaPipe that is developed by Google. And this library is dividing the human parts into 33 movement points. And these points, each point is a coordinate X, Y, Z, since it is a 3-dimensional environment. And from there, we can get our data. And this part, Mohammed will explain further.
So thank you very much. Thanks. So first of all, I apologize for the technical problem that we had at the first, and nobody could see the presentation. Can I continue? Okay. So, yeah, it's working. So basically, what we get from the media pipe and we extract the coordinates of the joint that this has been shown by my colleagues. So as you can see, we have a tabular data. The columns are coordinates of the joints, and total is 99. And the rows are the frames sequentially in time. So when I talk about the time, that means that our problem is somehow time series. And we have a lot of feature that moves and change. And that shows that we have a multivariate time series. But this is our raw data. can you please go to next slide? Okay, thanks. Working finally? Okay, so yeah, it's working. So we need to somehow change the data to the input and output that we would like to have for our modeling, basically. As you can see, our input can be the data for the past events. For example, here, past 4 events, the frames that we had, and we could predict the next frame. And that can be a hyperparameter, so we can have more, look more in the past, and we can predict more in the future. Generally, we try to predict just one in the future. After having our data, then we are prepared to go to modeling. And the modeling that we use is basically deep learning that uses LSTM layers. So it seems simple. Input comes to LSTM layers, can be multiple LSTM, bidirectional or normal, and then it goes to dense layers. Also, it can be very deep or not, doesn't matter, and we try several times. And then we have the outputs. So we are happy that maybe it's working. Yep. So as you can see, try to work it, we need initial movement. So this initial means here that this is the past and the memory of our input to generate a new data. So this is basically done by the human, and we want after that continue to new movements. And let's see what can we start as a next point. Yes, we somehow failed. It seems that the person go to the right and just starts there. But we're not disappointed, really. We are not disappointed. We are still hoping that making something better. So we decide to have a look at another model. So as you remember, I already talked about that our input, our output is somehow coordinates value directly. But what about being there just a distribution, normal distribution, for instance? Then instead of directly predicting the value, we just need to predict the features of the normal distribution. For Gaussian, just we need to know what is the mean and the standard deviation for each value. And we hope that that's working. And also we change the loss function accordingly as well. So let's see. And yes, yeah. No, our guys broke his leg. It's even worse than before. Yeah, but it's not end. It's not end. So, but what we are thinking is that maybe we can do something else. If we're thinking as the whole points in the body, it means that probably our dense movement somehow, for instance, if I move my heads, it's also related to the hands that I have. So instead of just single output, which is whole body, why I don't make them as a multiple? With all of the body, I use one model for the head, in parallel other models for the other part of the body. And interestingly, it can have a different models. Here we use all of them as the same structure and architecture. And what we got it? Oh, yeah. Our guys know moves at least. It doesn't seem very real dancing, yeah, somehow. But it at least moves. And the thing that it's show that the thing is that it shows that okay, after sometimes it become do the repetition. So I would like to go to the conclusion. It seems that the multi-part model that we called it are promising. Maybe as a future, somebody can use different layers and models for each part and then do the parallel. Or we can use more, let's say, dancer styles as an input, then the dynamic, probably dynamic, the first one changes. Maybe we can define a keyframe. What does it mean? That we say that, okay, start dance from this position, from the whatever it's a history, and give me the dance that has a, let's say, destination position. This is another idea. The other idea used other models. We had a very quick experiment on the TCN, which somehow have LSTM and convolutional neural networks. And it shows a little bit good at the first frames that we had also, but again, the repetition happened. So we would like to say our special thanks to Dr. Tristan Berens to be our mentor for his fruitful comments and discussions. We would like also to say our thanks to our DSR teacher for the insight that they're giving to us. And last but not least, we would like to say our thanks to batch 27 students or people that we had. Thank you for sharing your knowledge with us. Thank you for being our friend. So thanks for your attention. If you have a question, we are open to answer.
Right, so now while the next presenter prepares, we are going to read questions. Yes, we have to read questions. I just need to find one computer of the many that we have here that has the feed from YouTube. Ah, there, perfect. Yeah. Let me read from here. Breakdance, yeah, okay. Capoeira moves, definitely. Yeah. Yeah. So, okay, so it's mostly just nice comments, no questions. Anybody has any questions? So for me, I think the important part of this project is this idea of training a model for every part of the body, which is kind of very innovative, right? So most models take the data as a whole. And here what we are doing is, okay. It's to decompose, use the human intuition that, hey, this is a body, bodies have different parts and parts have their own properties. Can we train a model on every part, right? So I think this is a very interesting approach that these guys took. Oh, okay. Okay, let me scroll up because I'm reading tiny little text on a phone. Let me see.
Did you train only in one dance style?
Okay.
So yes, actually we did only train on one dance style, but it was for compiled 220 videos, about 10 hours of dance, because we didn't want to have much deviation in the output. So we tried firstly to do that with only 10 hours of one dance style, which is hip hop, I think.
Yeah, it seems one dancer, so she did a lot of different things. But this is one other idea that maybe later we can use other dances because the dynamics changes and maybe it's not so fast turning happening. I don't know. This is one idea for the future, but thanks for the question.
Right, so there's a comment from Kevin saying let's not put anything on Slack because the notifications are problematic. So I think we fixed that problem. So whoever had notifications with audio, we sacrifice as the first presentation for the technical problems. Thank you very much. Thank you very much. Okay, so for a second presentation, we have Antonio, who is a philosopher with a PhD from Cornell, going deep into the problem of whether machines can be creative if you feed them the same input that you consume as a human, and whether they can be useful for you to create your own art just by giving the machine the same input that you consume. So, Antonio?
Here I am. Buonasera. Hello. Guten Abend. Bonsoir. Sabah al-Noor. So, okay. So I guess are we ready? Yes. Okay. So my presentation will revolve around a very simple question. Simple and yet fundamental. Can machines be creative? So before all technologies jump off the chairs and tell me, no, they cannot be creative. Of course, a piece of metal with a bunch of numbers in it can never be creative. I would like to say, let's wait and see. So let's think about something. What is creativity? To answer to this question, I will propose 3 different definitions of creativity. One will be based on language, which means we're going to look at the root of the word creativity. Another one will come from one of the greatest artists of history, Michelangelo. Guess what? Italian. And the third one will come very modestly by me. So the first definition of creativity. What is creativity? Creativity comes from a verb. Oh yeah. Yeah, I have slides. Look. So creativity comes from a verb. Creare. What is creare? It's an activity. It's an activity, but activity of whom? Is the activity of a god. So creativity is an activity and therefore a skill and something that comes from a god. So every time we use the word creare or to create, we should really pay attention to what we're saying, because we are somehow implying that we are repeating the actions of a divine presence, a god. So there is a breath of the divine every time we create something, every time we bring something to life, something new. Second definition of creativity. I love this. It's from Michelangelo. People don't know that. Everybody knows this. This is David. This is the David of Michelangelo. Normally we used to look at David in his face, the front, the chest, the muscles. However, the beautiful part, the most beautiful part, is this, the back. So Michelangelo, what did Michelangelo say about creativity? He said, when I create and I have a block of marble, what I'm really doing there? I am removing the excess from the marble. So creativity is an act in which we remove the excess from the marble. So it's an iterative process. It's like a while loop, okay? While the piece of art is imperfect or unfinished, I continue to work until the piece becomes perfect, until the statue emerges from the block of marble. Third definition, more modestly from me. I have fun with words. I create words. I link them together. I write. And I've read a bunch of different things. And rather than what is creativity in general, I would like to say what is creativity for me, how I experience it. Well, whenever I have to create something, a new piece, I set an intention, look for words which are already contained somehow in my mind, or the sentences that I've memorized, that I know. And then I repattern these sentences into a novel combination. So to some extent, I'm using old things, words which are already there and present, but repurposing them for a new, in a new combination. So it's a process of repatterning. It's recycling, really. So this is how I see it. And what happens when I do that? When I get into the zone and I do this thing? Well, let's look at an example. I've been playing on Instagram a little bit. I paint portraits, but with words, which means I think about someone, I take a photo of this person, and then I try with my words to paint their essence, like with the brush of my pen. And this is something that I wrote for a woman I was in love with. So here it is. And it's actually longer than this. It says this: if you were an adjective, you'd be watery, moist, windy, tempestuous. If you were names, you'd be struggle, fall, madness, but also rise, success, redemption. Good art, bad art, good creativity, bad creativity. It doesn't matter. What it really matters is that these words that everybody uses normally now are put into a novel, original, decent combination. So can machines be creative? The answer is, I don't know. So I had to reformulate the question. Can machines help me be more creative? Can a model, again, a bunch of numbers thrown in a piece of metal, help me engage with my own creativity and produce something more interesting, more novel? And this is the origin of my project that I am Tecna. So normally, which is a text generator, basically. The idea is simple. Normally, when I hear about people engaging in language generation, we train models on the general knowledge, on a lot of books. But for me, I did something different because I wanted the model to produce something that looked like something that I would say, that I would think, even if I didn't. Sometimes I don't even agree with myself. So maybe the model says something that I don't agree with, but something that it's close to me. And so to do that, I built a data set with my interests, my favorite songs, some of my favorite books, some of my favorite quotes, things that crack me open, that make me want to cry, that make me jump because of joy, that make me want to dance. So I did that. And I'm going to give you a brief example of the things that I've used. For example, here, Alicia Keys, my muse. One of my favorite songs from Alicia Keys is Underdog. I sing a song from a hustler, training on the bus stop, single mothers waiting on a check to come, young teachers, students, doctors, sons of the front line who never gonna get a run. This goes out to the underdog. This is a song that makes me cry every other time that I listen to it. So she needs to be there. Then Jacques Kerouac. The only people for me are the mad ones. Mad to live, mad to talk, mad to be saved. Desirous of everything at the same time. Those who never yawn, nor say a commonplace thing, but burn, burn, burn like a bright yellow Roman candle. And then I have a third example and last, from Nikita Gill. We have calcium in our bones and iron in our veins. Calcium in our bones and iron in our veins, carbon in our soul and nitrogen in our brains. 93% stardust with souls made of flame. We're all just stars that have people name. And so take all this, shake it, and put it in a nice model. It's very simple. Embedding layers, LSTM. I played a little bit with LSTM, tried to stack multiple layers on top of each other. Couldn't improve the accuracy. Looks like the model works better when it's simpler. Simplicity sometimes, perhaps, or maybe it was just me, who knows? Anyway, got accuracy of 80%. Trained the model for maybe like 300 epochs. After 300 epochs, the model didn't perform any better. And this, everyone, is are some of the output that I got. I do not want you. Now I'm like you. I don't think I'm gonna dance for you. I'm so tired, girl. So my model is a little, sassy here. And then there is a little bit, the model gets a little bit deep. Pure is beyond altogether. And then there is my favorite one, of course. Love is the knowledge of the right things. And this is something that I really resonated with me because I worked on love for many years and I still think about those things. Huh? So what? Yeah. And yes, so here is where I stop. So thank you. Thank you, everyone. Thank you, colleagues, for this beautiful experience. And thank you to my mentor, Tristan, Rabbi. And yeah, if anybody has questions or curiosities or anything or not.
With the questions from the text. So one question from me. So you mentioned accuracy being 80%.
Yes.
How do you measure that? Is accuracy of what exactly? I didn't understand.
The accuracy of the model predicting the output. So
Right, the input I understand. The output is generative, right? So
generative,
it's
yes,
new, right?
yes.
So what is the accuracy measured on? So it's a generative model, so it's not trained on labeled stuff, right?
No, they're not training. Yeah.
Well, during the training, right. Okay, yeah. Mm-hmm. Right. Okay, let's see what else we have. Right, is 80% good in this case, says Kelly.
It's better than nothing, and it's a good start because what I really needed was to get out a little bit of sense. So I needed shards of truth as opposed to long sentences, something that could tell me whether this was going to be something interesting that I would pursue later. And the answer was yes.
Right, so
Lightsabers.
we have machines teaching us new moves, teaching us new things to say. Right? They're making us better for the girls, basically.
Yes.
Okay. So Tristan said that his fiancée, her heart is growing right now.
Oh, thank you. I really appreciate that.
Right.
Any?
Yeah, so Tristan says accuracies in generative models do not tell that much. Yeah, that was my thinking too. Cool.
All right.
Anybody in
Thank
the
you.
audience here has anything to say?
Anything to say? No.
Then, what?
No. Not yet. Not yet. I need a little more output for this. Soon enough. Soon enough.
So the question, sorry, they don't hear this.
Ah.
The question was if he has written a poem with Tecna. Yeah.
And the answer is, as I said, soon enough. Not yet.
Okay, so now we get to the next team that is going to talk about how to detect COVID from coughing sounds. So it's another use of machine learning for audio that is actually taking images as input. So the wave file is an image. And let me introduce you to the team well, they don't have a real name, Sujit, Tomek, and Paul. It's harder to say than the Mohammed.
Hello. So thank you very much. It's a pleasure for us to present our data science project in the DSR batch 27. Yeah, today we would like to present you the Covert Detector, which basically is a proof of concept to use complex machine learning technology and apply it to a complex biological biological system to get detected, and also for the diagnosis and in healthcare. So basically, this is our content. So we would like to give you a small introduction about respiratory diseases, how is diagnostic treated, what is the impact of these illnesses. We will talk about the data structure and the data source we have used for this approach, and also how to apply deep learning to this specific problem. We'll talk about results we get, and also the limitations, and how we can improve the scope, and also to put this approach in perspective to diagnostics approaches in general in healthcare. So now I would like to give the word to Sujit.
Hi, thanks, Paul. First, I would like to thank everyone for the last great 3 months, exciting learning, having lots of fun here. So I'll just talk about what's going on in the world, which obviously everybody knows that the pandemic has hit us really hard. But even before the pandemic, respiratory diseases are very, very highly prevalent in society, in the world. And if left untreated, obviously they will cause lots of serious damage. Lots of other diseases apart from COVID, like pneumonia, bronchitis, tuberculosis have been existing and devastating populations all over the world. And it has been very serious, especially for countries like India and Africa. So the problem we were thinking about was, would it be possible to distinguish symptoms just from the symptom, whether it's a serious one or just a regular symptom? So this is what we've been thinking. And in general, the business case was that COVID has been very devastating. As of today, almost 250 million cases have been reported, and around 5 million deaths have already been reported so far. It has devastated society in many, many ways, and almost 95 million people more went into extreme poverty last year, and around 80 million have been very undernourished and compared to pre-pandemic levels. So things are bad and they're getting worse, as you can see from the graphs. So the motivation for this project is that even though we can do tests in cities and the Western countries, rural areas are still suffering because there's very low healthcare resources available, and it's very difficult to access the symptoms. And pre-screening tools would be very useful to prioritize cases and reduce the load on the healthcare providers. So what would happen if we could have a tool which anybody can use, and it's in a phone and accessible to everybody in rural areas? So getting medical data is really hard. That's a big problem because of privacy reasons. Clinical trials are expensive. Getting the exact kind of medical data is not something that we can do as normal people. Healthcare institute or hospital, government has to be involved. So that was very hard for us to just get data related to respiratory diseases. So luckily, the Indian Institute of Science in Bangalore, which is akin to the RKI in Berlin in Germany, like the Robert Koch Institute, it's the premier health organization. They started a project called Koswara, which lets volunteers log in and record their own respiratory data with a questionnaire. At the end of the presentation, you can see how you could possibly contribute to this. And we were very lucky to have this small data set available, and that's what we used to try out our project. So the data source is basically sound data on 9 features like coughing heavy, coughing shallow, breathing heavy, deep, stuff like that. They're all given as WAV files, which are recorded by volunteers. So they are very different in terms of quality from each other. That's one of the problems. And the data set that we had was very unbalanced because only 56 corona positive cases were there in more than 1,300. So this was a huge problem for us to work on this. But yeah, we found a very unique approach to solve this problem. And the challenges we had to this product, to this project, well, there were missing data, which had to be taken care of, which is very important for any data project that you work on to start looking at that before. Then we had some nested structures, and normalization and reshaping the data was a big problem because all kinds of different sound files of different sizes and qualities were there, and we had to figure out how to make some kind of normalized sense out of it. And the last problem was the quantity. We would like to have a lot more data to make something commercially usable. And with that, I will invite Paul to Tomek to talk about our deep learning approach.
Hello, guys. Thanks a lot for taking the time to watch our struggles. Yeah, let me get into the technical part of how we approached it. So after some analysis, talking, consultations, we came to the conclusion that we should treat this problem as an anomaly detection problem. And that already narrowed down a little bit the scope of models and approaches that we can use. So to solve this problem, we picked Variational Autoencoder as the tool that will be most likely to help us and solve it. So what is a variational autoencoder? To give a deep explanation would need some more time, but talking generally, it is built out of 2 different models, one encoder and a decoder. The first one learns to represent an image into a latent space, and the second one, decoder, takes this latent space and out of it generates a reconstructed image. So our approach here was to train the model only on healthy cases, so only on data from the healthy people, so that the model knows how to reconstruct the healthy sounds. and then tested on a mixed data set of healthy and unhealthy cases with an assumption that it will do much better reconstructing healthy cases compared to unhealthy, and those would be treated as an anomaly. Yes, here we can see a little bit of a pipeline of how the data was processed. We started with wave files audio data, which were converted into MAL spectrograms. After some manipulations, reshaping, we converted them into tensors and fed them into the model, which doing the whole loop of encoding and generation gave us reconstruction as an image. And our approach here was having this reconstructed image. We take it and compare it to the input. So we look at both the input and the output and look at the differences. How, if the difference is bigger, we assume that it's an anomaly. If the difference is smaller, we assume it is a healthy case. Now Paul will talk a little bit about the results of how we did.
So I will take you through the results. Basically, here you can see that we trained our model like it is normal did in machine learning, like generating a training and a test set. Here we made a train validation split of 80% to 20%, basically meaning that we are training on 80% of the training data and uses 20% for a validation, just to see if we are able to train a model in a proper way, if we are overfitting it or not overfitting it, so that we have some control about the machine learning approach. Tomek or Sujit said already that we have a very complex data structure, and what we actually did, we have data from 9 different features. And the first idea was to see, okay, are we able to make for each feature a model and see which of these features, which is basically an attribute, for example, coughing heavy, coughing shallow, or breathing, might be important to generate an algorithm which is able to detect the positive samples. Personally, I was curious about which of this feature might perform better than the others, since also from the Cosvara project, it was not really clear which of these features might be have an impact on the machine learning models. So at the end, we were training our model with, we are creating 9 different models based on these samples. And at the slide, you can see an example of a training of a model in which we have used the coughing heavy data. So basically what you can see is that on the y-axis we have a loss number, which is indicating the construction loss, and basically what we expect during training, that the loss will drop after epoch. Which basically means that after each iteration, the model is like learning, and the reconstruction will be better. In this case, you can see a line in orange, which is the training data set, and in blue, the validation set. And basically what you can see here is that the orange and the blue line is like dropping more or less the same. So we can assume that our model is training for the training set in a similar manner to the validation set. Okay, so next step would be basically to test our model in a prediction way on data it hasn't seen. So what was like the test data set we generated. And the test set generated, we generated in a way that we tried this time to make a balanced data set. So we took each 56 positive cases we are able to get out from our data, and supplemented it like with 56 other healthy data. and then try to make a prediction and see if our models are able to catch and to detect in the right way. So what is the result? So now of the 9 models was able to predict with a higher accuracy of 60%. Basically, we're asking ourselves, okay, so what exactly happened here and why is this the case? And you have to, I would give you an example, which we call the coughing challenge. And basically, I would like to play you a sound so that you will understand the challenge of generating a model from this kind of sound data. So you hear now the healthy cough. And now we can play a sound from a COVID patient. So what we can distinguish, so there is a difference, obviously, from both. But for the model, it's a really complex task because, as you can see here, it's not only the sound by itself, which is in a complex way different from each other, because we have these kind of breaks in which there are milliseconds of non-tone and then the sound of the cough. But even there's a much more complicated situation because each person has a different tone, different amplitude, different color of his voice. So when he is coughing, this is also causing problems, which is basically a very general problem if we are making diagnosis in healthcare, that we have taken a random sample, of course, but we always have to think about that each individual is different. And this is putting noise into our system. So on the data side, what we can do, what are the limitations in the outlook? So the medical sound data are complex and inhomogeneous. This is the main reason or the main challenge for us. So the knowledge of sound characteristics and how to manipulate sound in a pre-processing step is crucial to detect the similarities and differences, which basically says that there must be a knowledge about how to treat a very specific sound sample. So playing around with the sample size, with the length, with the sample rate, with window slices, and also the normalization and scaling. But there's also another side, which is I would say machine learning is not enough. Basically, domain knowledge is as important as machine learning skills to address complex diagnostics challenges in healthcare sector. We can see here that one feature is not enough to treat it with a machine learning approach and expecting to get out an approach which is detecting it in a very high accuracy. So basically, experts has to investigate which features are important, which symptoms are important to look at. Must there be engineering or re-engineering of the features, which features we have to select and extract, but also how to combine features, for example. And this would also be for us, for our Covert detector, a perspective in which you would say, okay, so we have not only to work on the sound, but also to have to think about how we can combine features, how we can implement multiple features in the model to improve our Covert detector. So in summary, what does it say? Machine learning can be a very powerful method also in healthcare and in diagnosis. But at the end, it's also important to have the experts, the people who are doing the clinical trials, to provide us data which are meaningful, and also people who are working in laboratories. And also the physicians who have to treat and to interpret symptoms and give a hint which might be important and which not. So I would close our presentation. I would special thanks to our mentor Tristan and also Mohammed, who was doing a lot of coding work and helped us really a lot to make even this baseline, because as Tomek said, we were struggled and very often and in different points, and he was very helpful. Of course, I would like to thank the whole DSR 27 batch for fantastic 12 weeks in which we learned, we were laughing, crying. So thank you very much for this great journey and great experience with you guys.
All right, so while the next team prepares to present, let's go for questions. Sorry. Tristan says, I almost got infected just listening to the sample. Okay. There are no questions. Okay, in which case I have one, right? So if it's very difficult for the normal trained person to diagnose COVID just by listening to coughs, we should not expect probably to get models that can do that better than humans, right? Is that the intuition, or is there any reason to believe that a model can beat human performance? Well, actually they do, right? So in perceptual tasks, they're better than humans at some things.
I think there's also a second layer, basically, which is saying if you are ill, for example, and you do not feel right, and you're coughing, so maybe you're not, but me, I'm always thinking, okay, is it something serious or is it just an infection? Should I go to the doctor or not? And this might be a problem for people which do not have this easy access to medicines. And that's why we think that this might be an important pre-screening approach, which is saying, okay, go to the doctor if the machine learning approach is thinking you have something serious. Because as you maybe also know, if you do not treat even you feel good, but you're not treating some issues, then it might be getting worse. And this is the idea of saving capacity in the healthcare system.
Right. Now there are apps like Ada, which is in Berlin, that ask people questions about what they are feeling and so on. They could use something like this to listen to cough instead of asking, right? That's pretty cool. Yeah. Awesome. So thank you very much.
Thank you very much.
All right. So for the last presentation of the day, we are going to look into how machines can help you program synthesizer sounds. So maybe not that many people know this, but programming sounds in a synthesizer is very hard. So if you want to mimic the sound that you just heard, it's very hard. Very few people can do this well. And the question here was whether a machine could do that and could give a superpower to beginner synthesizer programmers, which there are many of them, including myself, to basically replicate a sound that you hear without having to break your head against a wall and tweak your parameter until you get it right, which could be hours. Right, so that's the Diva team. And they are about to get ready. There is a little bit of feedback. They have a very complicated setup. So you will hear a real synthesizer, a real analog synthesizer, and a real person who knows synthesizers play with it. So, okay, now we get the audio from the synthesizer. Yes. Yeah. Cool. Sound check. I hear myself, which is kind of going to be disturbing for the presenters. So just the setup of this presentation takes a good hour at least. So that thing you hear is an analog synthesizer that replicates a famous design that it's very old by now, 40 years old. You may recognize it from some techno music that you listen to. It has a signature sound. It's a Core MS-20. And Diva is the name of Great. So sound check is passed? No? No? Ah, okay. So we're going to get audio from back and forth from the computer to the synth. I mean, can you show the looks like it works. So this thing that you're seeing right now is the Core MS-20. Okay, so we are good to go, right? Okay, so here's the Diva team, which is Sebastian, Graham, and Maud.
Good evening, everybody. So let me check if this is working. Okay. Hi, everybody. I'm presenting our Deep Diva project that we worked on the last month. It's an automatic synthesizer programmer. And maybe I start off a bit about explaining what I should know hold this thing, how a synthesizer programmer works. And some of my colleagues here in class, I must say I was a bit surprised, like they didn't have an idea what a synthesizer was. So I came up with this picture. This is a synthesizer, for example, kind of a complex one. Arun, can you show the other one here? This is also a synthesizer. Basically, it looks like a piano. Current and turns it into sound, okay? So the thing about a synthesizer is it's a very abstract instrument, so to say. You have a lot of knobs that basically transform the sound. So you have a lot of different knobs. Some of them have hundreds of knobs, so to say. So each set of knobs, each setting produces a unique sound. Okay, so this is a background. And if you say you want to program a synthesizer, it basically means I find a certain sound using the knobs in a certain way. Okay, you can imagine that this thing is from the 70s. So nowadays, actually it's in replica. It's pretty new, but you can imagine that nowadays these things are also in software, right? So the Diva, the name for our project, is coming from a software synthesizer. So it exclusively runs on computers. It has a GUI. If you watch the slide, this is how it looks. You can still see it has something to do with knobs. Yeah, it still has knobs. This particular synthesizer has about 400 parameters. And yeah, to program it can be a hassle. For a lot of people like me, it's fun. So I would never think about automating this. So why should I? It's the thing is just, if you think about companies that sell musical instruments and who's actually buying these things, nowadays more and more amateurs, so to say, are able, get the tools to be really able to produce their own music. That's a thing that happened in the last 20 years. To record your music, the microphones, the sound cards, all the instruments, they got really cheap. With computers now, you have your own studio at home. And so what happened is that these tools, they were used by professionals in the 80s or 70s, right? Who had a big budget. Nowadays, a lot of amateurs sit in front of these thousands of knobs and actually know nothing about it. But still, they want to use this, right? And the way you get around with this now is there's something like presets. So a preset is nothing like a super small text file that actually just remembers how you put the knobs in which position. So when you buy a synthesizer now, you get hundreds of presets. If they're not enough for you, you buy new presets. There's like $10, you get presets for horror movies, okay? And then you skip through the presets until you find one that you like. So this way you can program a synthesizer without knowing basically anything about it. But then again, there's some restriction to this approach, right? Imagine you have a certain idea of a sound and it's pretty, and you already know the sound because, for example, on one of your favorite songs, it's in that song. Or you have some recording of that sound. So the idea to automatically program the synthesizer here, in this case, is I would show the sound to some tool, and then this tool will output the preset that I can load into the synthesizer. So to say, our neural net knows how to twist the knobs of a certain synthesizer, in this case, the Diva, and shows me how I can actually use this sound. So this is pretty straightforward now, describing our approach, right? If you have this this thing here, we input a sound wave. We kind of transform this stuff. Maud is going to talk more about this. What is wrong? You don't see this thing? Oh, that's a pity because it's beautiful. Okay, so right, we have the sound wave. We input it in a net, and it outputs us not a sound. That would be an easy misunderstanding of the project, but it outputs a preset that is just a vector of a whole lot of numbers that make up the creation of a sound in a synthesizer. Okay, so how would we go about this? Of course, every good model can only be trained if you have good data. So how do you find data? In this case, you can actually make the data yourself because there are some tools. We found a particular one programmed by somebody. It's called Renderman. It's basically a tool you can use from Python that accesses your VST plugin, which in this case is our software synthesizer, and it renders sounds from Python. So what we can do, we make a loop and we just randomly generate presets, knob positions, so to say, and then generate audio for them. And we decided to do this for 2-second bits of audio. So now we just let it run through the night and let it generate 100,000 different knob positions, sets of knob positions, with the respective audio. And we kept all of this on our hard disk. So this was basically the data set we were using. Later, if you have questions, we tried a lot of stuff. We tried to make massive data sets or smaller ones. So we ended up with this because it kind of gave us the best result. I think now Maud will explain a bit more how we actually transformed this data to put it into the neural net.
Thank you, Sebastian. Can I have the pointer? Yeah. All right. So I think I'm a little bit smaller than Sebastian. All right. Also, thank you for everyone joining online. So basically now we ended up with a data set consisting of audio time series, but most deep learning models don't deal with audio in its raw form. So we actually, for our project, extracted 2 types of features from our data set. So audio is usually converted into an image by generating a spectrogram. And a spectrogram basically shows the amplitude against the frequency. So what we're looking at now is we're looking at sound in the frequency domain. But the thing is, we as humans don't actually hear frequency or the pitch linearly. So actually what we had to do is convert our spectrograms to a MEL spectrogram, which reflects more as how we humans hear the sound. And in a similar way, also we as humans don't hear amplitude or the loudness of the sound linearly. So again, we had to further convert our spectrogram with a power to decibel scale so that the sound is really like how loud we hear it. So we ended up with MEL spectrograms that are a visual representation of the sound the way we as humans perceive it. So the brighter the color in the image, the more power a certain frequency has at that point in time. And then we also normalized our MEL spectrograms before we use it in our model training. All right. Then a second type of feature that we extracted, which is related, is also a time frequency representation of audio or MEL frequency substrate coefficients. And these are a compressed representation of the spectrum of an audio signal. And these MFC coefficients contain information about the rate of change in the spectral bands. All right, so our aim was to train a model that could reconstruct the patch, aka the combination of synthesizer parameter settings that generates the original sound. Now, with extracting our features, we actually changed our audio problem into a computer vision problem. So we could actually use algorithms that also perform particularly well with images. But there's also a different way that we could look at features like the malfrequency substrate coefficients, because you could also see them as a time sequence. Because audio information usually also follows a pattern. So we could also try out sequence models. And this is what we did in our project. We experimented with 2 different neural network architectures. So on the one hand, we tried out different convolutional neural network architectures that tend to work particularly well for images. And then we also used a bidirectional LSTM with highway layers. The bidirectional part basically allows the model to access the complete sequence, both in forward and reverse order. And the highway layers provide a way for information to flow through the layers of the model uninhibited, and at the same time also through the kind of standard means to nodes with the activation functions. So apart from experimenting with these different neural network architectures, we also experimented with varying the amount of synthesizer parameters that were allowed to be randomized. So basically, we're varying the complexity of our problem and see also how that influenced the model performance. And then otherwise, we also experimented with training parallel models. So basically, we're grouping the synthesizer parameters according to their function, so in what way they influence the sound. And then we actually trained different models in parallel, predicting each of these different groups of parameter settings, so allowing these models to specialize. But at the end of the day, most of our models actually performed fairly similar, and we actually ended up having to restrict the number of synthesizer parameters that were allowed to vary to actually have a reasonable model performance. But this is actually consistent with also another project out there in the literature that kind of tries to tackle a similar problem using a different synthesizer. So it just turns out to be a complicated problem. All right. So I'm just going to briefly discuss with you our model architecture of kind of the final model that we're presenting to you tonight. So we're using our MEL spectrograms as input into a convolutional neural network that consists of 4 convolutional layers intertwined with max pooling layers. And we have 2 dense layers and an output layer at the end. All right, so our model predicts a vector of numbers corresponding to the synthesizer parameters that generate the sound. And these are compared to the actual synthesizer parameters that were used to generate the input sound. And so when the true patch and the predicted patch are very similar, or the difference between them is very small, that is a good prediction. And we used as a loss function, we minimized the root mean squared error between the true patch and the predicted patch in our model. And also what you see here is kind of a visual representation of how our training loss and validation loss behaved across training. And as you can see, around the 75th epoch, we kind of started to overfit and discontinued actually. But we were saving the model weights in between. So the model that we're actually using tonight is the one where the lines kind of cross over. All right. So we actually evaluated our model using different measures. So we looked at the mean absolute error between the true patch and the predicted patch. We looked at comparing the MEL spectrogram of the true sound versus the predicted sound and the difference between them. And of course, we actually listened and just compared the sounds. So what I'm going to do now is actually show you 3 different samples to give you a bit of an indication how well our model is performing. So what you can see here is the MEL spectrogram of the true sound, the true test sound. And Graham is now going to play how the actual true sound sounded. Oh. Put back on the sound. All right, so that is the true sound. Yeah. And what we're gonna play to you now is the sound that was predicted by our model. those, well, I don't know how the quality of sound was online, but those are actually quite similar. And you can also see that when you compare the true and the predicted Mel spectrogram and the difference between them. Actually, the mean absolute error between the two Mel spectrograms is relatively low. All right, so we have another sample for you. Again, this is the Mel spectrogram of the true sound, and this is how it sounded. Left click. Oh. Left click. All right. Beautiful synthesizer sounds. All right, so that was the true sound, and now again we're going to play to you the sound that was predicted by our model. There we go. Okay, so again, not too bad. And as you can see, the two Mel spectrograms of the true and predicted sound look quite alike. But when evaluating our test samples, what we actually also found is that our model has some difficulties with certain sounds. So what I'm going to play to you next is, again, a true input sound, and then I'm going to show you how our model performed. So, yeah. Yeah, exactly. I think we have a little delay in here. All right. No. You can play it? Does it work now? Maybe go back. Just to avoid confusion. Oh. Maybe play it once. So that, I don't know if you heard it, but that was the true input sound. But this is actually what our model predicted. Now, this is actually a little bit different, and that's also what you can see here in the true and predicted Mel spectrogram. And also in the mean absolute error, you can see there's a lot more error in there. But up to this point, I've showed you, or we evaluated our model based on test sounds that were generated by the Diva synthesizer. And we're now going to go over to an actual live demonstration, and we're going to challenge our model, and we're going to input a sound coming from a different synthesizer, namely this one.
Cool. So I'm just getting the file sent to me right now. Very live demo. I'm very ready. Was born ready. This is Apple's fault, actually. It's AirDrop. There we go. Came through. So now I'm just gonna walk you through the web app that we created here. So it's very basic. You can see just the the interface is very basic, but all the magic is in the back end. So I'll just input the file that was just sent to me. Live demo, nice, very nice name. Okay, so here we can, so our model only takes in a 2-second clip. So what we have to do is tell it where to start the clip from. So I'm just gonna start from the start and then input a file name, live demo, that was great. Okay, and now when I click this, it's gonna send it to the back end. It's gonna run it through our whole model pipeline, create a prediction, and then hopefully send a preset back to us. Oh, and we get a very nice little cat GIF too. Just cherry on top, you know. Okay, so now we have this preset, as you can see, it's downloaded on our computer right here. So what I'm gonna do now is get rid of the cats for a second. I know you guys love them, but put this into our Diva. So bear with me 1 second. Here we go. So here's our Diva. And so we want to go to live demo. This is the configuration that our model actually predicted. So now what we're going to do is listen to the predicted sound. As we can see, Sebastian is a little bit concerned at what is predicted, but don't worry. This is a different synthesizer to what we actually trained it on. So that's our bail. Oh, it's all good. You can't hear it anyway, so don't worry. Okay, bit of technical issue. Let's see. Is anybody good with computers? Can you help us? Play it again. All right, let's try this. Ooh, okay. Maybe it's just the suspense issue again. It's just waiting. Low volume. You want to try that one? Ah, there we go. So that's what we were waiting for.
That's what I was actually seeing before you heard it. So this sounds super different, but in terms of this, the synth is actually just slightly wrong. There's just this knob. He just found it. There's a thing. If you don't input sounds into it, that it's directly coming from the Diva, but from somewhere else, there are some issues still, because I suspect it has something to do with the model being a bit spoiled, because we gave it stuff that was kind of similar in volumes and cropped in a certain way. And I think if we go from external, this is the main reason this has these problems.
Yes, never spoil your model. Okay, so I'll just talk a little bit about the future of our product. So firstly, as you can see, we might need to improve the sound matching quality a little bit. Now, this is a constraint from a couple things. So firstly, we're only using about 11 parameters. So that means we can't really predict very complex sounds or anything like that, really. So we hope to improve that to the full array of parameters, which is about 281, I think. And secondly, the model also prefers some parameters to others. So we want to kind of even that out a little bit as well. So another really exciting avenue that we could go down is to test out something like a variational autoencoder, right? Quite hard to say. So how that would work is we would put a embedded layer of, we would embed the Diva synthesizer in the decoder part. But there is a little bit of a caveat to this, because the parameters that we receive from the Diva aren't actually differentiable. So as we all know, we need differentiable weights in our neural nets. So that's a bit of a hard issue. But we are inspired by another project that is called Deep AFX. So it's trying to solve a bit of a different problem, but they have been able to solve this undifferentiable issue. So then moving on to the product, as Sebastian said, yeah, what we set out to do was to create a product where somebody could put in any synthesized sound, and then the arrangement would be on the dashboard of like the configuration. Currently, we can only put in about 2-second clips and just a single pitch. So I think in the end, we'll probably have a mixture of models, an ensemble, if you will, and that would probably then be better for varying lengths and varying pitches. And then finally, we'd really like more of an integration with the Diva system. So as lovely as the web app is with all the cats and everything, it's probably not the easiest interface to use. So we really would like to make it more integrated with Diva, maybe like a plugin or something like that, really. Okay, so that concludes our presentation. However, I think we probably want one last thank you to everyone. So a very big thank you to Tristan. I think you've been mentioned in every single one of these. You're an amazing man. So yeah, Tristan and everybody in the DSR family, all the participants, all the teachers, Jose, everybody. Thank you very much. This has been an amazing journey. We've had so much fun. Yeah, so thank you very much.
Awesome, really cool presentation. People are partying already, so before they go and party, we have food and drinks. Let's go through questions or anything in the chat. Tommy, can I see the chat, please? Goosebumps, okay. So, Shashank, can you show the output? What do you mean, Shashank? Okay, while people clarify the question. So Florian asked, why the Diva Synth? Well, because it has filters and oscillators from many analog beats from the past, including this MS-20. So it can emulate a bunch of different sounds, right? I mean, I'm answering the question, but actually Sebastian is true.
No, what was the question?
Why Diva?
The Diva is one of my favorite personal synthesizers because I like the sound of the 70s a lot. And yeah, it's exactly like this. The Diva is like closest to emulating the old analog sound, like this fat sound. So I was super interested in working with the Diva for this project. And yeah, it's the main reason. And also, like a lot of people who are into this right now in the world, they are focusing on FM synthesis because logically FM synthesis is so much harder to program. So if we have a net that can do this for us, it could even help the pros. But we wanted to do something else, like go on some field where the others are not like having food all the time.
Right. So is this like Shazam but for synthesizer sounds? Yes, right. That's a good way to. I was thinking about this.
This is probably Mohammed. So Mohammed, for many days, he insists this is Shazam for synthesizers.
Bunch of fancies.
Okay, if it's, I give this to you. This is Shazam for synthesizers.
Cool. Okay. So people are saying goosebumps, tears to my eyes, DSR family, and so on. And to this, I have to say, the Slack group for alumni is kind of dead. So we have to resuscitate it somehow. I think we have to do something because people do have this feeling of family, but at the same time, you graduate and we barely hear from you ever again. We send email and people don't open videos that we carefully crafted for you. I don't know how to fix this problem. It's a hard problem. We don't do community very well. Party, okay, yeah. Eating and drinking together should have this problem, right? So let's do just that, right? But okay, so if there are no more questions, this was DSR 27 demo day. Thank you so much for your attention and hopefully see you around. Yeah.